Alright, now we're going to finish out our reactions of alkenes, and we're going to start with what is known as epoxidation. So epoxidation is one of those reactions that is definitely more important for organic chemists. It's not something we really see biologically. And you'll see why in a moment based on what the product is. Now, while there are a number of reagents that you can use for this reaction, the most common one is one that's known by its acronym, MCPBA. And it converts an alkene into an epoxide. An epoxide is this three-membered ring with an oxygen in it. And so epoxides themselves are not necessarily the most useful species, but as we'll learn when we get to the chapter that deals with ethers, we'll see that it's very, very easy to do things with epoxides. So how does this reaction work? Well, in order to see the whole reaction, we need the full structure of MCPBA. Which is this structure here. Known as meta-chloroperbenzoic acid. And the alkene in it will react in this way. And that's the entire mechanism for the reaction. And it gives us an epoxide. Again, when we get to the chapter on ethers, we'll talk about what we can do with them. Another reaction that we can do with alkenes is the formation of syndiols. So a syndiol would be a diol, so two alcohols. They're going to be on adjacent carbons, and they're going to be pointing in the same direction. Now, the most common way to do this reaction is to use a reagent known as osmium tetroxide with NMO. The NMO, which I'm going to draw here, this stands for N-methylmorpholine. N-oxide, doesn't ever react with the alkene. Instead, what happens is after the osmium reacts, you get an osmium byproduct that's no longer reactive. And so the NMO reoxidizes the reduced osmium byproduct so it can react with an alkene again. And the reason that you need to do that is osmium tetroxide costs about $100 a gram. But this reaction goes through what's known as an osmate ester. And because this intermediate here is cyclic, that's why we end up with both alcohols on the same side. And then you add NaHSO3 along with water, and that breaks the osmate ester apart to give you your diol. Now, you can also use potassium permanganate for this reaction, and potassium permanganate is a lot cheaper, but the control is generally a lot more difficult. So even though osmium tetroxide is very, very expensive. It's also a very sensitive reagent. You actually have to store it in a nitrogen atmosphere. But osmium tetroxide is very easy to control, whereas potassium permanganate will sometimes do what you want, but will sometimes also continue to destroy your entire molecule. All right, two more reactions to look at here. We have alkene cleavage reactions. So these are reactions that we are going to completely break apart the alkene. And the reaction that we're going to look at here is known as ozonolysis. So one of the neat things about this reaction is it's really, really easy to monitor. Ozone O3 is blue, and as soon as you add it into your reaction mixture, it'll react with the alkene and the blue color goes away. So as soon as that blue color stays, you know that your reaction is complete. You also generally have to run this reaction cold, negative 78 degrees Celsius. And we're not going to do a mechanism of this reaction. The reason I'm not going to cover a mechanism here, this is an extremely complicated mechanism. In fact, this mechanism actually showed up on my final in one of my organic synthesis classes in grad school. But it forms what's known as an ozonide intermediate, which you then add zinc and acetic acid to. You don't want to isolate these ozonides, they are explosive. And as a result, it literally cuts your alkene in half. And on each carbon of what was the alkene, you end up with a carbonyl. Right, now our final reaction of alkenes are going to be dealing with a class of molecules known as carbenes. Carbenes are very unusual carbon species. They are neutral carbons that have 6 electrons. And so typically they are sp2 hybridized. They have an empty p orbital. And they have a lone pair. So this would be the simplest carbene we could have. So you can see it's a carbon, it has 2 hydrogens, it has a lone pair, and an empty p orbital. But carbon, we know, wants 8 electrons, we know it wants 4 bonds. These are extremely reactive. And often they're actually too reactive. So for the reaction we're going to look at here, we're going to look at what we call carbonoids. And carbonoids are species that basically have the same behavior as carbenes, but they're a little more controllable. And the reaction where we see them is known as the Simmons-Smith reaction, which has been around since 1958. So in this reaction, we take diiodomethane and react it with zinc and copper to make the species that is known as our carbonoid. Once you add this to an alkene, that carbon, which would have been the carbene, or the carbene-like species, will react with the alkene to form a cyclopropane ring. So the Simmons-Smith reaction allows us to convert alkenes into cyclopropane rings. So at this point, that is the end of our reactions on alkenes. And you'll now want to try some of these reactions, do some practice. So you should get out in-class exercise number 20, which has a number of different practice problems, all of which deal with the reactions of alkenes.